we looked at how to solve non-homogeneous linear equations using the method of undetermined coefficients. So if you remember, for undetermined coefficients, let me see, undetermined. So we looked at the case where all our a's, an of x, an minus 1 of x, and so forth, all the way to a0 of x. These are all constants, the case we looked at for undetermined coefficients. And another thing, we consider the form where g of x has the form e to the kx, maybe cosine of kx, sine of kx, where k is a constant. And we looked at when it has the form of a polynomial, say ax to the power of m plus bx to the power of m minus 1, all the way to maybe some constant, or some combinations of these functions, or functions of this form. So it turns out that undetermined coefficients, the method of undetermined coefficients, works when we have this kind of formulation, or this kind of format for our a's and the g. So in other words, there's a constraint to the method of undetermined coefficient. We're going to explore another method called the method of variation of parameters that doesn't necessarily have this kind of constraints. So let's look at, I'm going to summarize the method. Summary of method for variation of parameters. So I will explain as I write the steps involved in the method. Step 1, and I'm not going to prove anything, but I'll try to explain. So first of all, we have to make the coefficients of yn 1. So in other words, we have to go on here onto this equation, and we have to divide through by an of x. So if we divide through, so make coefficient of yn unit, so make it equal to 1. So if we do that, we end up with yn plus maybe pn minus 1 of x, y of n minus 1, all the way to maybe p1 y prime plus a0 or p0, now p0 of x, y is equal to, instead of g of x, let's now call it f of x. So after dividing through by an of x, I renamed whatever we have p's. So pn will now be 1. Okay, so that's the first step. Step 2 would be to solve the homogeneous version of this equation. Homogeneous version. So the homogeneous version is to just make f of x 0 and then solve the equation. And assuming we solve the homogeneous version and we get what we call our complementary solution, so to get the yc, let's say yc will be c1, c1 times maybe y1 of x plus c2 y2 of x, all the way to cn yn of x. Okay, this should be familiar to us. So the next step, I'm going to call it step 3, is to compute the following determinants, the following Wronskians, if you may. So compute W, W1, W2, all the way to Wn. And I'm going to define each of these W's. W1 is just the Wronskian, or W, sorry, is just the Wronskian of the Y's. So is Y1, Y2, all the way to Yn. Of course, if it's just Y1 and Y2, then you have a 2 by 2 matrix, and that would be a nice situation. And then the next row is their derivatives, Y1 prime, Y2 prime, all the way to Yn prime. And then you keep going until the n minus 1 derivative, Y1 n minus 1, Y1 n minus 1, Y2 n minus 1, all the way to Yn n minus 1. So that's the definition of W. Now, we need W. W1 is similar to W, but how do we define it? What we do is on the first row or the first column, we have all zeros. On the first row, we start with 0, we ignore Y1, then we do Y2 all the way to Yn, right? And then second row, 0, Y2 prime all the way to Yn prime. And then we keep going till we do Yn, actually Y2 n minus 1 all the way to Yn n minus 1. But now, instead of putting 0 here, we put f of x. Okay? So we follow the same pattern to define our Y2 now. Y2 would be something similar, but instead of putting the zeros in the first column, we put it in the second column. So we have Y1. On the first column, we have our Y's, our Y1. So we have Y1, Y1 prime, all the way to Y1 n minus 1. And then the second column, now we have zeros because we're dealing with Y2. Zeros all the way to here, we put f of x. And then the remaining columns are just the same kind of thing. So Y3 prime all the way to Y3 n minus 1. And then we go to all the way Yn prime. Keep going, Yn n minus 1. Okay, so that's Y2. You define Y3 in a similar version, and YK. So let's keep going all the way. So if you have any YK, would be, you just make the kth columns 0. So you have your Y1, Y2, maybe here you put 0 and you keep going. And then you have Y1 prime, Y2 prime, you put 0 there, all the way to Yn, Yn here. So let's make it a little bit more. So this is it. Oh, so that is 0. No, that's not what I want. 0. And this is YK plus 1. YK plus 1 prime. Keep going all the way to Yn, all the way to Yn. So I'm trying to be as general as possible now. And then you have So take all the derivatives. So here we have y1 n minus 1, y2 n minus 1 all the way, and then here you have your f of x there. This is yn minus 1 of k plus 1 all the way to yn minus 1 of yn. Okay, so this is a general definition of this Wronskians. So basically, how do you find these W's? Just go to the column. If you have W1, go to the first column, put 0 in everything except the last entry. Replace the last entry with f of x, you know. So you take your W, right? This is how W is defined. You go to the column corresponding to the number, and then you replace everything with 0 until you get to the last entry in that column. You put f of x in it. All right, so we know how to define our W's. There's a lot of explanation involved in that W, but we're not going to bother ourselves with that. So that's step 3. Let's look at step 4. Step 4 is to define the following. Step 4 is we're going to let U1, we're going to define U's, what we call our U's. U prime, U1 prime is W1 over W. U2 prime is W2 over W, and so forth. Un prime is Wn over W. Okay, so these are the derivatives of our U. So all we have to do now is integrate each of these to obtain U1, U2, all the way to UN. And then the last step, step 5, is let YP be equal to U1 Y1 plus U2 Y2, well, all the way to UN of x, Yn of x. So if this is your YP, then the general solution of our equation is y of x equals yc plus yp. Okay, we're going to explain this more with an example. Okay, we're going to explain this with an example. Because there's a lot involved in it, I know. Let's call it example 1. Maybe we can get 2, but let's start with 1. Let's try to solve 2y double prime plus 8y is equals to 6 cosecant of t. So first of all, step 1 is to divide through, make the coefficient of yn unit. So we're going to make the coefficient of y double prime unit. Step 1, divide through by 2, so we end up with y double prime plus 4y prime, plus 4y is equal to 3 cosecant of t, right? So what did we do? We divided through by 2. All right, step 2. We solve y double prime plus 4y equal to 0. So our characteristic equation is r squared plus 4 equal to 0. So this tells us that r is plus or minus 2i. And if that's the case, our yc is going to be c1 cosine of 2x plus c2 sine of 2x. All right, we're very familiar with how to solve homogeneous equations with constant coefficients. Okay, so the next step is to compute our Wronskians, I think. Let's look at it. Yes, our Wronskians. So I'm going to compute W. W is cosine of 2x sine of 2x, right? So this is your y1, y1, y2. So cosine of 2x, sine of 2x, and then its derivative, negative 2 sine of 2x, and then this is 2 cosine of 2x, I believe. Yes, I think I'm right. So this is a determinant. We're computing a determinant. So the determinant is going to be 2 cosine squared 2x plus 2 sine squared 2x. This is just going to be 2. If you factor out the 2, you're left with cosine squared x plus sine squared x, which is just 1. So this is 2 cosine squared 2x plus sine squared 2x. So this is 2, okay, because this is equal to 1. Okay, very good. Now, that's W. So we need W1 and we need W2. W1 is, we go to our Wronskian, we put 0 here. The in the first column we put 0 in the first entry, and then the second entry we put our g of x, or what we call our f of x here. So f of x, or f of t actually in this case. So I'm going to put 3 cosecant of t. All right, and then we have I need to be careful. I started with t's and then I ended up with x's. Where did I get my x's from? So let me just make it x instead of t's. Make it x, and that will solve my problem since I can't keep track of my stuff. I keep mixing up t's and x. Okay, so all right, so this is x, cosecant x, and then the second row is second column sine 2x, 2 cosine 2x. So we compute this Wronskian. So it's just gonna be, well, it's not technically, it's no longer Wronskian, but you know what I mean. So this is just gonna be negative 3 cosecant of x sine of 2x. Okay, that's scary, but it may not be as scary as it looks. Now we do the same thing. So this time now we have cosine 2x negative 2 sine 2x, and then we have 0 there, and we have 3 cosecant of x. So in this case we get 3 cosecant of x cosine of 2x. Okay, so we need to find u's now. So u's, that's step 4. U1 prime is w prime is w1 over w. Okay, so u1 prime, so that's step 4, what I called step 4. You can call it whatever you want. All right, step 4, u1 prime is equal to w1 over w is equal to w1 over w is equal to -3 cosecant of x sine of 2x all over 2, and u2 prime is w2 over w is equal to 3 cosecant of x cosine of 2x all over 2, I think. All right, so to get our u's, we need to integrate each of this. U of x now, or u1 is the integral of negative cosecant, -3 cosecant of x sine of 2x all over 2 dx. So it's just going to be let's see, cosecant is 1 over sine. All right, and sine of 2x, let's see, sine of 2x is, so let's factor the constant first. So cosecant is 1 over sine of x, that's easy. And sine of 2x can be written as 2 sine x cosine x, okay, dx. So this is actually -3 integral, things are going to happily cancel out, integral cosine of x dx. So this is just -3 sine x plus a constant, but don't worry about it. We usually don't put the constant in there, just like when we do integrating factor. And we can discuss why we don't need a constant, but we can do that in class, or just send me an email and I'll help you out with that. U2 now is going to be integral 3 cosecant of x cosine of 2x all over 2 dx, and this is integral cosecant of x. We can write it, let's factor out the 3 over 2. We can write this as 1 over sine of t, and then the cosine of 2x, we can write that as we can actually write that as 1 minus sine squared of x. I want x here, not t. Okay. Yes, definitely. All right, and then we have the x. So this is integral integral cosecant of of x minus sine of x. And I have 3/2. 3/2. Yes. Sine of x. Okay. I have a feeling that I've messed something up, but I'm sure you guys are going to let me know in the comments. So let's put this. Let's have this 3/2. 3/2 is here. Okay. So we have this cosecant of x. Its integral is actually, if you look it up in the integration table, it's natural log of cosecant of x minus cotangent of x. And it's actually something we can do, but let's just go with the table. And then we have 3/2 cosine of x. Okay, so that's our u2. So the step 5 is the last step. To find our yp, we have our yc and our yp. So yp, step 5, yp of x is going to be u times y1. What is u? u1 times y1. So first of all, let's get our y1s and y2 in order. y1 is just cosine 2x. So it's going to be u1 times y1. u1 times y1. Let's not be lazy. Let's put of x, y1 of x, plus u2 of x times y2 of x. y1 of x is, okay, cosine 2x. So we have -3 cosine 2x sine x, and then plus, that's u2, u1 times y1, plus sine 2x times this gigantic thing. What we can do with natural log of cosecant of x minus cotangent of x plus 3/2 cosecant of x. All right. Okay, so that's our u. So if you notice any mistake, please just don't be afraid to just leave a comment there for me. All right. So yp, general solution is y of x equals yc of x plus yp of x. So yc of x is this. Copy it. So y of x. Paste. Oh no. When you copy and you don't paste it, you lose it. That. Copy. No, I didn't want to do that way. Copy. All right, so paste. That's yp. And then plus. That's yc, sorry, plus yp. This is yp, copy. P. Yep. Plus this. Let's squeeze it up a little bit. Put it right here. All right, that works. Then maybe make this a little large. Okay. So I think that's all we have time for. So this is our general solution. I was gonna do a second example, but let's stop. Let's leave it at this. All right. I'll see you in the next video. I'll see you in class. Um, Please, I would like you guys to take a look at everything I did and make sure you're satisfied with it. All right. Later.